Hello everyone. In the previous session, we studied about the first order low pass Butterworth filter. So now in this session, we'll continue with the fifth module. Next, we have second order low pass Butterworth filter. So this is the configuration of the second order low pass Butterworth filter, and this is the frequency response of the same. So frequency response will remain the same, except for which the roll-off factor will be equal to minus 40 dB per decade. And the first second order low pass Butterworth filter is obtained from the first order low pass Butterworth filter by adding an additional pair of the R and C as shown here. The second order low pass filter is obtained from the first order low pass filter by adding an additional pair of R and C as shown here. So this is the configuration of second order low pass Butterworth filter, and these resistors R1 and RF will determine the gain of the filter, and these resistors R2 and R3 along with the capacitors C2 and C3 will determine the high cutoff frequency FH of the low pass Butterworth filter. And now the high cutoff frequency is given by 1 by 2 pi into square root of R2 R3 C2 C3, and the magnitude of the second order filter is given by magnitude of V0 by Vin is equal to AF by square root of 1 plus F by FH whole power 4. Power 4 because it is second order. If it were to be first order, it would have been power 2 here. Since it is second order, it is to the power of 4, where FH is the high cutoff frequency, F is the frequency of the input signal, and AF is the passband gain of the filter. Next, filter design. Frequency response of the first and second order is same except for twice the roll-off rate in the stop band. I discussed about this previously. Next, the steps. First step is we are going to choose a value for high cutoff frequency FH. Then step 2. Here we are going to equate the resistors R2 and R3 equal to R and the capacitors C2 and C3 equal to C. Why this is done? In order to simplify the design calculations. So we'll set R2 and R3 is equal to R, C2 and C3 is equal to C, and then we'll choose a value of C such that it is lesser than or equal to 1 microfarad. Now we know C and we know FH. Okay, from this formula we'll calculate R as equal to 1 by 2 pi FH into C. So from this formula, we'll calculate the value of R. So now we know high cutoff frequency and the capacitor C and the resistor R. Now step 4, what is it? Now in second order filter analysis, one thing you should remember is that the passband gain AF is equal to 1.586. So this RF, see this now, AF is equal to 1.586, isn't it? So 1.586 is equal to 1 plus RF by R1. So RF by R1 will be equal to 0.586. So RF is equal to 0.586 into R1. So this is the necessary condition for if the filter has to exhibit Butterworth response. So we need to consider this important or necessary condition such that RF is equal to 0.586 R1. Now we know R1. How? We are going to choose R1 such that it is less than or equal to 100 kilo ohm. R1 is the resistance that we have here. Here it is responsible in determining the gain of the filter. Okay, so this value of R1 we are going to choose in such a way that it is less than or equal to 100 kilo ohm, and we'll substitute this value of R1 in this particular equation and find out the value of RF. So now we know all the values in the that are involved in the configuration of the second order low pass Butterworth filter. So designing is over now. Next we have frequency scaling. Frequency scaling is the same as we discussed in first order low pass filter. That is any one component, either R or C, that is responsible in determining the cutoff frequency is supposed to be multiplied with the ratio of the new cutoff frequency by the initial cutoff frequency. So frequency scaling is the same. Based on this you might get some problems to solve, and here we have a problem to solve. Design a second order low pass filter at a high cutoff frequency of 1 kilohertz. Draw the frequency response of the network also. So this is the first part, and drawing the frequency response is the second part. So how are we going to solve it? First let us solve this part A of the question, that is the designing part. What is the step 1? We are going to assign a value for FH. So since they've already given FH is equal to 1 kilohertz, so we'll write the same, FH is equal to 1 kilohertz. Next, step 2, we are going to assume the value of the capacitors C2 and C3 as equal to 0.0047 microfarad. It should be less than or equal to 1 microfarad. We have assumed this as equal to 0.0047 microfarad. And we know FH, we know C. From the equation of FH, we'll find out the value of the resistor R, that is equal to R2 and R3. So we'll get R2 and R3 is equal to 33 kilo ohm. Next, we will fix a value of R1, and then we'll find out RF from RF equal to 0.586 R1, which is the necessary condition for the Butterworth response. So here we have assumed R1 as equal to 27 kilo ohm, and RF will be equal to 15.82 kilo ohm from this condition of the Butterworth response. Next, we have to find out, this is it about the design part. So now we have found out, we have got the values for RF, R1, R2, R3, C2, C3 and FH. Now draw the configuration of second order low pass filter, and draw the frequency response also, and indicate FH, and mention the value of FH against it, and after drawing you mention the values that you got in the circuit drawn against the respective parameters. Next, we have to draw the frequency response of the network. So in order to draw the frequency response of the network, first we need to find out the magnitude. First we'll tabulate this column, this table. First column will be frequency, second column will be gain of the magnitude of the gain. Next will be magnitude in dB, that is 20 log V0 by V in. So we will tabulate it for the frequency ranging from 10 Hertz to 10 kilohertz. So at 10 kilohertz, the gain magnitude is equal to, calculate FH we know. F is, substitute F equal to 10 Hertz. Next, AF also we know. AF is equal to Yeah, AF will be equal to, sorry for the disturbance, AF will be equal to 1 plus RF by R1 since it is the non-inverting configuration. See here, we are giving input signal to the non-inverting terminal. So here AF will be equal to 1 plus RF by R1. Okay, first find out this AF value and then you substitute the value directly. And yeah, from frequency ranging from 10 to 10 kilohertz, go on substituting 100, 10, 20, 50, 100, 200, 700 and 10k, and calculate the respective gain magnitude and magnitude in dB, and plot frequency versus gain in dB. And next we have first order high pass Butterworth filter. So this first order high pass Butterworth filter is obtained from the first order low pass Butterworth filter just by interchanging the resistor and the capacitor that is involved in determining the cutoff frequency. So this is the configuration of first order high pass Butterworth filter, and this is the frequency response of the same. So here it is allowing the higher frequencies and it is attenuating the lower frequencies, and this is the cutoff frequency FL. And since this is first order, the roll off rate is 20 dB per decade. This is pass band since all the frequencies in this particular range are passed, and this is stop band since all the particular frequencies in this band are attenuated or stopped from being passed. Next, now and coming to the analysis of the circuit, here we are supposed to find out the first step is we are supposed to apply the voltage divider rule at this non-inverting terminal. So here this is the non-inverting terminal and the voltage at non-inverting terminal is V1 here, as you can see. So by applying voltage divider rule, we will get V1 as equal to the voltage across it is Vin into the resistance is R divided by R R minus J into Xc. The reactance across the capacitor is minus J Xc. So it will be V1 equal to V in into R by R minus J Xc. Now I'll take this J Xc as common in the denominator. So I will get V in into R by minus J Xc into R by minus J Xc plus 1. Next, here also I have 1 by minus jxc, and in this term also I have 1 by minus jxc. So 1 by minus jxc can be written as j by xc, because 1 by minus j can be written as j, and we know that xc is equal to 1 by 2 pi fc. So this term minus 1 by jxc will be equal to j2 pi fc. So I will substitute 2 j2 pi fc here as well as here, that is underlined in the red pen. So v1 will be equal to v in into r into 2 pi fc by r into this part 2 pi fc plus 1. Next, upon simplification, we will get V1 as equal to V in into JF by FL by JF by FL plus 1. This is the voltage at the non-inverting terminal. Now, this particular voltage, that is the input voltage, will not be considered as the input voltage by the op amp. Instead, the voltage at the non-inverting terminal, that is V1, will be considered as the input signal to the op-amp. So here the output voltage will be equal to V0 will be equal to gain times the input signal V1 that we found out initially by applying the voltage divider rule. So V0 will be equal to gain times V1. So V0 will be equal to gain is AF, input voltage is V1. So gain, since it is a non-inverting configuration, it will be 1 plus RF by R1. So just for your understanding, I have written V0 is equal to AF, substitute for V in. Here we have substituted, and V0 by V in, that is the gain, will be equal to so much, where AF is equal to the passband gain of the filter, and F is the frequency of the input signal, Fl is the low cutoff frequency of the filter, and magnitude of this is AF into F by FL by square root of 1 plus F by FL whole square, power 2, because it is first order high pass filter. One main thing you have to make a note of is, in first order, here magnitude will have power 2, and in the roll off will be equal to 20 dB per decade, and here we'll have only one pair of R and C. So this is the important observations that we are supposed to make, and this is a problem that you are supposed to solve. Try to solve it, and you are also supposed to plot the frequency response of the same. Next, we have second order high pass Butterworth filter. This second order high pass Butterworth filter can be obtained from first order high pass Butterworth filter just by adding an additional component, or it can also be obtained from the second order low pass filter itself by interchanging the resistors and capacitors. Now, this resistors R1 along with RF will determine the gain of the filter, and these capacitors and these resistors R2, R3 will determine the low cutoff frequency. Same, everything is the same. Just describe the circuit and write few sentences regarding the same. And voltage gain magnitude will be given by this equation, which is equal to AF by square root of 1 plus FL by FL to the power 4, because it is second order, and gain will be equal to 1.586. Passband gain for Butterworth response, second order Butterworth response, will be equal to 1.586. So the key points here are, the roll-off factor is 40 dB per decade. Okay, and then here we have two pair of resistors and capacitors. So this is the important observation from the circuit diagram and the frequency response that we are supposed to make for second order high pass Butterworth filter. And from the equations here, to the power of 4 will let me know that it is second order. And for second order Butterworth response of the filter, the passband gain should be equal to 1.586. This is very, very important. You are supposed to remember this. And this is one more problem that you are supposed to solve. As we solved for the other filters, the same method is supposed to follow by you people, and try solving it. And if you have any doubts, please do ask me. I'll clear it within a short period of time. And after solving, make sure that you get values for C, FL, and R, and F as so much. Now, one more. See here, from first order low pass filter, we can easily derive or get the configuration of second order low pass filter by just adding an additional R and C. Okay, next, now if I want to draw the configuration of first order high pass Butterworth filter. Now in the first order low pass Butterworth filter itself, I will interchange the R and C and I'll get the first order high pass Butterworth filter. Now if I want to get second order high pass Butterworth filter from the first order, I'll just add additional pair of R and C. If I want to get second order high pass filter from the second order low pass filter, I'll just interchange the resistances. So from first order, if you want to get second order, interchanging of the resistors and capacitors should be done. If you want to get second order from the first order, adding additional pair of R and C, this mismatch has to be done. Just you see the configuration of all the circuits, you will come to know it is very easy.